Hi. So I'm here to start a lecture on Chapter 14, and Chapter 14 is all about rates of reaction, and the rate of a chemical reaction can be defined as the change in the concentration of the species divided by the time during which that change takes place. So, as an example, if I wanted to express the rate of the chemical reaction as presented here, I would say that the rate is equal to negative change in concentration over the amount of time that that change takes place. And so the reason I would call it negative here is because the reactant is going to decrease, and so since there will be a decrease, the value you would calculate for a change in concentration would be negative. So you want to take the negative of the negative to make it positive, because your rate should always be a positive value. And I can also express it in terms of the products. And so in this case, it would be the change in concentration of the NO2 relative to the time, but I have to divide it by 2 here. And then the same thing for the oxygen, change in concentration of the oxygen divided by 1/2. So what I've done is I've taken this equation, I've reduced it down to the simplest balancing coefficients. And then when I describe my concentration, it's the change in the concentration of the N2O5, but it's also the change in the concentration of the NO2. But because of the different coefficients in the balanced equation, their concentrations don't change at the same rate. So in order to make the rates equal, because for the reaction there is only one rate, in order to make the rates equal, I have to divide them proportionally. So because there's twice as much of this as there is of the reactant, I have to divide that change by 2. And since there's half of much of the oxygen as there is of the N2O5, I have to divide the change in the concentration of the oxygen by 1/2. Okay, so now here I just have this set of data, the data table above. You can't read, so it's written out here. So this is an example of what happens. So as time progresses, you can see that the concentration of the N2O5 continually gets less and less. Okay, and so as the concentration gets less and less, the rate gets slower and slower. So what we know then is that the concentration, in this scenario at least, the concentration has its greatest impact on the rate of the reaction, because as the amount decreases, the rate slows down. And so that's what you'll see with your rate values. So this table here shows the effect of the concentration of rate of a reaction by measuring the initial rate with respect to one of the reactants. So I'm just going to point out what the table shows, and then you can kind of read through my detailed descriptions of what happens. So you can see here, we're going to look at series 1 first. You can see here that in this reaction here, all right, this is the one that I'm talking about, I need to hold the concentration of one of my reactants constant, which makes sense, right? In order to figure out how one reactant affects the rate, you're going to have to just change one at a time. That's what this effectively does. So as I double my concentration of the hydrogen, I can see that the rate doubles. As I triple it, I can see that the rate triples. And as I quadruple it, I can see that the rate quadruples. So that all makes sense. Okay, now I'm going to see what happens if I hold the concentration of the hydrogen constant and I do the same thing to the concentration of the NO. And so in this scenario, when I double the concentration, the rate quadruples. When I triple it, it goes up 9 times. And when I quadruple it, it goes up 16 times. So what's the difference here? So this is a very direct relationship. This is an exponential relationship. So how do we describe that? So I'm going to go down here. So the way we describe that is we want to talk about the rate in terms of some rate constant times the concentration of one of the reactants raised to a power of how that rate changes. And we'll do the same thing for the hydrogen. So where do we get those values from? So what we can see is that the concentration changing of the hydrogen is going to have the same effect on the rate. Concentration changing of the hydrogen is going to have this exponential effect. So then what we're going to say is that the rate of the reaction is affected differently by each of the reactants. So for the first one, we can see that when we changed the concentration of the hydrogen, all right, we saw that there was that direct relationship. So I'm going to raise the hydrogen to the power of 1, n. That's just a variable. And then for relative to the NO, I can see that it's squared, all right, that exponential effect. So that M value would be squared. And so I know that with respect to NO, we call this the order of the reaction is 2. With respect to the H2, the order is equal to 1. And so I would identify this reaction with an overall order of M plus N, which is going to be 2 plus 1. Okay, so finding these values of M and N are the tricky part. Adding them up to equal 3, oh, that's pretty straightforward. Okay, so how do we get these numbers and how can we follow a calculation method in order to calculate this order value of M or N? We'll only have reactions that have 2 reactants in our studies, so you'll only ever be solving for M and N. So if I have this decomposition reaction, as you see here, all right, so I have this decomposition reaction, and the rate of decomposition is measured at different concentrations. So what I see is that if I have 0.1 molar, this concentration, we're going to assume it's molarity, and if I have it at 0.2, 0.3, and 0.4, the rate at 0.1 is low, a little bit higher, a little bit higher, a little bit higher. So that's what we said when we first started here, that the more of the reactant you have that's being analyzed, then the faster the rate would be. Or as the reaction proceeds, the rate slows down. So what we want to do is we want to find the order of the reaction. So what we do is we look at, we write out what we call a rate expression. And this would be a rate expression for experiment 2. Okay, so for experiment 2, I know that rate 2 is equal to K, that's my rate constant, times the concentration of 2 raised to the M power. And then then I would write it for another one. I need to compare. In order to find a rate expression, I really have to have data to make comparisons. So for rate 1, I would plug in the values that I have for rate 1, okay, rate 1 there, and the concentration. So those are the two expressions that I would use. So now I can rearrange that to say that the rate 2 over rate 1 is equal to the concentration 2 raised to the m power over the concentration 1 raised to the m power. So now I plug in the data in order to, because I know that the K value is going to be the same, right? K is always constant as long as temperature is constant. At this point, that's what we're considering as constant temperature. So I'm going to plug in the values from my data table. So for rate 2, I'm going to plug in 0.081. And for rate 1, 0.02. And then I'm going to plug in the corresponding concentrations. So it's 0.2 for the second one, the second experiment, and it's 0.1 for the first. And those values are all raised to the power of m. So how do I solve for m? Because that's the order of the reaction. That's going to tell me by what factor this rate progresses based on that reactant. And there's only one reactant in this case. So I do my math here and I find that this expression is 4 equals 2 to the m power. How do I solve for m? To solve, I mean, it's obvious that it's 2 raised to the second power. But if they weren't such obvious, if it wasn't such an obvious arrangement of values, then to solve for m, I would use this expression. I would say the log of 4 is equal to the m log of 2. And then I go through the algebra, plugging in my logs and solve for m. But I find out that my m is equal to 2. So now I can say, this is the ultimate goal with this little problem, is what is my rate expression? My rate expression is this. The rate of this chemical reaction is equal to K, some constant. All these rate expressions have a constant. And my concentration, whatever the concentration is of my reactant, raised to the second power, which is what I used my data to solve for. Okay, so now what you do is you just go back to your experiment and use experimental data to solve for the K. So let's look at that for a minute. So what am I going to do? I'm going to pick one of my experiments to use. So I'm going to pick the first one. And I'm going to say the rate is 0.02. So 0.02 equal to K plug in the concentration in that first trial, raise it to the second power. And now you should be able to calculate from that what your K value is. So if I do that quickly, if I take 0.1 raised to the second power, and then I take 0.02 divide by 0.01, I'm going to get 2. So my rate constant here is 2. So now you've gone through and you've solved for your rate constant. So now, how do you find the rate at some random concentration? So let's say we just want to find, it's not any of the values that's plugged into my table up here, but it's just some random value of concentration. Well, I now know, so in order for me to find the rate at some random concentration, I'm going to plug in my K value of 2, because that's what it's going to be all the time for the decomposition of that reagent. And so now I know that my concentration is just a random one that I've picked raised to the second power. So to solve for the rate here, I would just take my 0.15 concentration that I'm interested in, raise it to the second power, and multiply by my constant K. I'm going to stop there.